Chapter 11, Part 3, last lecture video of Gen Chem 1. Woohoo! Alright, so first two lecture videos were all about intermolecular forces and then how those intermolecular forces impact their physical properties. This last little bit is kind of cleaning up. We're switching gears. Okay, we're looking at other things. So, we're going to be looking at phase changes. So when things go from solids to liquids, or liquids to gases, or gases to solids, or gases to liquids, or liquids to solids, or all the other scenarios. Okay, so when something is changing its state of matter. So just a reminder on some vocab with this. But when we're going between a solid and liquid, that can either be melting, which is also called fusion, or freezing. Liquid and gas, we can be vaporizing or condensing, and then a gas and a solid can either be subliming or depositing, sublimation or deposition. And back in chapter 5, we talked about the terms endothermic or exothermic. So when we're changing the state of matter, we're either adding heat or removing heat. So if you've got a liquid and you want to make it a gas, you have to add heat to it. You got to put it on the hot plate, okay, or put it on the stove. If you've got a solid and you want to make it a liquid, you've got to add heat to it. But if you've got a liquid and you want to make it a solid, well, when you take water, you put it in ice cube trays and you put it in the freezer to make it a solid, liquid becoming a solid, we are removing heat, energy is being released, so it's exothermic. So all the arrows that are blue and pointing down are all exothermic processes, and all the arrows that are red and pointing up are endothermic processes. If they're red and they're pointing up, that means they have to absorb heat, which means you got to warm them up. If they're blue and they're pointing down, that means they need to release heat. They've got to cool down to do whatever process is happening. So heat is an important part of phase changes. If you want something to change its state of matter, you have to add or remove heat. And just a reminder, I feel like I shouldn't have to say this, but I'm saying it anyway. Just because something is a certain state of matter in one situation doesn't mean that's the only state of matter that it can be, right? H2O is a liquid at room temperature, but it can be a solid and it can be a gas. So some chemicals can change between the different states of matter. So we're going to be focusing on these phase changes. Okay, so it turns out to change the state of matter, again, there's energy that has to be involved, some heat that has to be involved. Well, each chemical has its own number for how much heat it takes to do these states of matter changes. So heat of fusion is how much energy it takes to turn a solid into a liquid. Heat of vaporization is how much energy it takes to turn a liquid into a gas. Heat of sublimation is how much energy it takes to turn a solid directly to a gas. Now, of these three, the one that takes the most energy, well, heat of sublimation takes the most energy because going from a solid to a gas, that's a giant change. Solids and gases are very different from each other, so it takes a lot of energy to make that happen. The one that takes the least amount of energy is the heat of fusion. Melting something takes less energy than boiling something or subliming something. So down here at the bottom, it just gives you a little graph showing you just some examples of the numbers of each of these. So the orangey pink ones are the heat of fusion, so that's melting. The blue ones are the heat of vaporization, which is boiling. And the green ones are the heat of sublimation, which is subliming, so going from solid directly to gas. So there's obviously a big difference there between fusion and vaporization. And then there's, for a lot of them, a dramatic difference between vaporization and sublimation. Okay, so it takes energy for these things to happen. If you were going the other direction, if instead of vaporizing, going from liquid to gas, you're going from gas to liquid, all that would change was these numbers would be negative. Because negative is what a negative number with energy implies it being released. So when heat is being absorbed, these values are positive. When heat is being released, these values are negative. Okay. So just a quick reminder, when we've dealt with heat before back in chapter 5, we dealt with this beautiful equation where M stood for mass, C stood for specific heat, and delta T stood for temperature change. And Q stood for heat. Okay. This works great as an equation when we're changing the temperature of something. But when we're doing a phase change, the temperature doesn't actually change. When water is boiling, it stays at 100 degrees Celsius the whole time it boils. So when you're boiling your water on the stove to cook your macaroni and cheese, once the water gets to a boil, it's going to stay at 100 degrees Celsius. It's not going to change, okay? So there's no delta T for a phase change. That means this equation doesn't work for phase changes. This is just for temperature changes within the same state of matter. So I take water, or I take a liquid, and I warm it up or cool it down. I can use this equation. Take a solid and I warm it up or cool it down. I can use this equation. I take a gas and I warm it up or cool it down. I can use this equation. But if I'm taking a liquid and I'm trying to make it into a solid, I cannot use this equation because there will be no delta T, no change in temperature while it is freezing. So we have to have ourselves a new mathematical equation that takes into account these heats of vaporization, these heats of fusion, and these heats of sublimation. So in some ways it looks like the other one. So Q equals Q for heat, N, which if you think of chapter 10, that stood for moles. And then delta H of fusion, vaporization, or sublimation. Those are the heats of vaporization, of fusion, or sublimation. You would use whichever one you would need in the question. So I'm going to change this. It'll be fusion or vaporization or sublimation. Because these numbers are in kilojoules per mole. So for water, it takes 41 kilojoules per mole to boil it. So this equation just lets us cancel out the unit moles by multiplying it by the number of moles to get our answer in kilojoules. This is the equation we use when we do a state of matter change, which more concisely are called phase changes. There's no delta T because the temperature doesn't change, but there definitely is heat involved with that. If you want to boil water, you got to keep it on the stove. You shut off your stove, the water's going to stop boiling. So there's definitely heat involved. It just doesn't go with a phase change. If you don't believe me, take an ice cube out of your freezer, put it in your hand, grab a thermometer, just like a thermometer that you measure to see if you have a fever or not, and put it on the ice cube while it's melting in your hand and measure the temperature. And that ice cube is going to stay at 0 degrees Celsius the whole time it's melting. Now, once it's completely went from solid to liquid, and all of it's a liquid, then it'll start warming up because then we're doing a temperature change within the same state of matter. But while it is going between solid and liquid, the temperature doesn't change. That's why we need that second equation. So this is called a heating curve. This is just taking into account how much heat it takes to heat something up or cool something down, and we're looking at situations where we both have using both equations, where we have a temperature change within the same state of matter, and when we have a phase change. So on this graph, the two horizontal lines, this one and this one, are phase changes. And if we look at the graph, the X value is getting bigger, it's taking heat, but the temperature, the Y value, isn't changing. So for water, well, at 100 degrees Celsius, that's when water's boiling. So it takes heat, but the temperature doesn't get bigger than 100, so it just stays flat. The blue ones, here, here, and here, are, down here is when, well, I take an ice cube and I warm it up from negative 25 degrees Celsius to 0 degrees Celsius. It's an ice cube the whole time. So I can use the Q equals M times C times delta T equation. But then I gotta melt my ice cube. So that's the Q equals N times delta H equation. So I melted it, now it's a liquid. Now I can warm it up between 0 degrees Celsius and 100 degrees Celsius using the Q equals M times C times delta T. Once I get to 100 degrees Celsius, I can't make the liquid any warmer. I have to boil it first. So there's me boiling it. And then the last step is me taking water vapor and going from 0 degrees Celsius to 125 degrees Celsius. So I guess I'm going to number these. 1, 2, 3, 4, 5. This would be a 5-step process. If the question said, calculate the amount of heat. Step 1 is taking a solid ice cube and going from negative 25 degrees Celsius to 0 degrees Celsius. That would be using the specific heat equation for step 1. For step 2, I'm melting. This would have me using the Q equals N times delta H of fusion. I chose fusion because fusion is melting. Oops. Step 3 is going from, as a liquid, from 0 degrees Celsius to 100 degrees Celsius. That would be the Q equals M times C times delta T equation. keep going the wrong direction. I'm sorry. So that gets me to right here. Then I've got to go, I'm at 100 degrees Celsius. I got to boil this sucker. 4. I need to boil. That's going to be Q equals N times delta H of vaporization. And the last step is taking the steam and going from 100 to 125. So I'm going to say gas instead of steam. And it's going from 100 degrees Celsius to 125 degrees Celsius. So it's using that equation. So one thing I want to do is I want to come up with another scenario. We're going to stick with water. But I want us to figure out what I'd have to do to calculate the amount of heat it would take to go from 13 degrees Celsius liquid to 111 degrees Celsius gas of H2O. So when we do H2O, I'm going to assume that you know the temperatures that are important for water. That water freezes at 0, water freezes and melts at 0, and water boils and condenses at 100. Okay, so we've got to think through the steps of this. I've got a liquid at 13 degrees Celsius, and I need to make it become a gas at 111 degrees Celsius, and I need to figure out how to calculate that. Well, I'm going to kind of map it out. Well, I'm at 13 degrees Celsius, and I'm a liquid. What's the warmest I can make water, and it still be a liquid? So in other words, when does water become another state of matter? Well, if I'm warming it up, 100 degrees Celsius. So step 1 is going to be for me doing 13 degrees Celsius water to 100 degrees Celsius water. At 100 degrees Celsius, I can't warm it up to 111 yet because it has to become a gas first. So I need to boil it. That's going to be step 2. And I'm still at 100 degrees Celsius. Okay, because when I boil it, the temperature didn't change. But I've got to get up to 111 degrees Celsius. So that's going to be step 3. So it's going to be a 3-step process. Step 1, I'm not going to do the math right now. I just want us to decide which of the 2 equations we need to use. It's either going to be Q equals M times C times delta T, or Q equals N times delta H. Well, if I'm going between 2 temperatures, it's going to be the delta T one. Number 2, it's going between 100 and 100. So there's no delta T. Which one do you think this is going to be? Delta H fusion, delta H vaporization, or delta H sublimation? Or boiling, so that's vaporizing. And then step 3, we're going between 100 and 111 degrees Celsius. So this is what I want you to be able to do. I'm not very likely going to ask you to actually do the math for this, but I'm going to ask you to map it out. Kind of like what happened here. So being able to recognize when you need to change states of matter versus when you just need to heat it up. So if it's something other than water, I would have to tell you in the question what the important temperatures are, like 0 degrees Celsius and 100 degrees Celsius for water. I'd have to give you that for the other equations, or for the other chemicals. So the last thing we have in chapter 11 are phase diagrams. So we talk about things like melting point and boiling point, and the temperature that something goes from solid to liquid or liquid to gas, these are actually subjective to pressure. So in high altitudes, water boils at a different temperature than it does where we're at, which is pretty much, St. Louis is pretty much right at sea level. Okay, so we're pretty much at normal conditions. So if you've ever baked a cake or cupcakes or something like that, if you look on the back of the box, if you used a box mix, on the back of the box, there's usually instructions for high altitudes. Have you ever noticed that? There's different cooking instructions because at high altitudes, they're higher up, they're in the mountains. There's less atmosphere pressing down on them because they're closer to the top of the atmosphere. So they're at lower pressure. The temperature that water boils is a lower temperature. It doesn't boil at 100 degrees Celsius. It boils less than that. So that's going to change how you need to cook stuff, because water, when it's boiling, it's making all the bubbles, but it's colder than when we boil water here. That's why, like, their hard-boiled eggs are kind of rubbery and gross, because of the temperature of their water. So phase diagrams are let us, if the pressure is something different than 1 atmosphere, which is what we assume it is all the time, phase diagrams let us figure out when something goes between, what the temperature things change between their states of matter. So we're going to learn how to read a phase diagram. So this one has everything labeled for us. So in a phase diagram, it's always going to be broken into 3 sections. There's going to be some lines going on here. When something's a solid, when something's a liquid, when something's a gas. The x-axis is always temperature, and the y-axis is always pressure, because those are the 2 things we're looking at. So it's going to go from left to right. Solid, liquid, gas. Okay? If you think about it, lower temperatures are solids, and as the temperature gets bigger, it goes to liquid and then gas. So left to right, solid, liquid, gas, I think makes sense. So if we've got our solid section and our liquid section, the line right here that's touching them, well, that's when something changes between a solid and a liquid. So that's when something melts and freezes. Okay. If I've got my liquid section and my gas section, the line right here separating those, well, that's when something's going between liquid and gas. So that's when it's vaporizing, which is boiling, or condensing. And then down here, there's a line between solid and gas. That's sublimation and deposition. Okay. Normally, these things aren't labeled. It's not going to say that word or that word or that word. It's not going to say those words on those arrows. There's just going to be lines. Okay. But those are all important things for us to know. The last 2 things that are important for us are the triple point. The triple point is the one spot on the graph where, when I put my pencil there, oops, it's touching the solid, the liquid, and the gas all at once. So triple. Chemicals have 1 temperature and 1 pressure, where it's possible for them to be in the solid, well, not when they are in the solid state, the liquid state, and the gas state all at once. So at 100 degrees Celsius, water can be a liquid or a gas because it's going to be boiling or condensing. So it can be 2 states of matter. At 0 degrees Celsius, it can be a solid or a liquid, or solid and a liquid. But at the triple point, it's going to be all 3. Okay, so the triple point is this one specific pressure, whatever that would be on the graph, and this one specific temperature, whatever that would be on the graph, in which that chemical is a solid and a liquid and a gas all at once. That's called the triple point. The other important spot is right here. It's the critical point, because there's these lines, right, between the solid and the liquid and the gas. But this one just like abruptly stops. This one goes to the end of the graph. This one goes to the end of the graph. This one stops. So it's the spot where we can no longer tell the difference between liquids and gases. It's the last place where I can clearly distinguish a chemical as being either a liquid or a gas. Beyond that point, we get this supercritical fluid. Think kind of like plasma. It's when it's either a really gaseous liquid or a really liquidy gas. It's hard to draw the line on when it's a liquid and when it's a gas because it's kind of this mixture of both. And so the critical point is the last time we can divide between liquids and gases, and that again would have 1 temperature, whatever that would be, and 1 pressure, whatever that would be. Okay, so this, well, it's saying everything I just said about the triple point and the critical point. I got excited about this. And that's states of matter, blah, blah, blah. Okay, so here's one for water. Okay, and it actually has like numbers on the axis and stuff. So the shape looks a little different, right? Like the shapes that these things make are a little different. That's fine. But they're still solid, liquid, gas, left to right. This one is giving you more information than you would normally have. Okay. The triple point for water, if we just looked at well, that's a beautiful line there and there. They very thankfully, based on the lines that I drew, told us what the conditions are to get water to be a solid and a liquid and a gas all at once. We need to get the temperature to 0.0098 degrees Celsius and the pressure to 0.00603 atmospheres. So it's possible. 0.0098 degrees Celsius, that's just like the freezing point. 0.00603 atmospheres, that's tougher to do. Normal pressure is 1 atmosphere. There are labs where you can do this inside of a plastic syringe. I've just never had good luck with that. The critical point is 374.4 degrees Celsius and pretty much 218 atmospheres. So 218 times more pressure than our atmosphere has, and a pretty high temperature. Remember, that is in degrees Celsius, not in Kelvin. I know Kelvin temperatures are big numbers. To convert this into Kelvin, we'd have to add 273.15 on top of that. So it's going to be pretty hot and very high pressure. So under normal conditions, the pressure is 1 atmosphere. Well, when I run into the line dividing solid and liquid, whoa, unsurprisingly, that's at 0 degrees Celsius, because isn't that the temperature that water melts? And at 1 atmosphere, the dividing line between liquid and gas, if we look at this scale, well, 50, 100, 150, 200, so that's at 100 degrees Celsius. Makes total sense, okay? But if our pressure was lower than 1, it would have a lower temperature between liquid and gas, so water would boil at a colder temperature. That was a dramatic one. It's not 50 degrees Celsius to boil water in Colorado, but there's definitely a difference. And the reason why these are all different all have to do with the van der Waals forces. But what I want you to be able to do with this is look at one of these and answer questions about it. Like if I give you a temperature and a pressure and say, what state of matter is it at this temperature and this pressure, that you can connect the points and see where it is. Or what temperature does it boil under this pressure? So just showing you, here's carbon dioxide. So just another phase diagram. So again, solid, liquid, gas, left to right. The shape is definitely different. The triple point for carbon dioxide is negative 56.4 degrees Celsius, so cold, but the pressure is 5 atmospheres, so not quite as high. The critical point is way easier to get to for carbon dioxide than it is for water. And at 1 atmosphere, sorry, my dogs are barking. That was not a straight line. Scenario we see is between solid and gas, which is why carbon dioxide goes from the solid state to the gas state. That's dry ice. So be prepared to read a phase diagram. So on the discussion worksheet, I've got some examples I want you to practice. Okay, so yay, chapter 11 is over.